Good evening, my dear friends. Welcome to our cozy channel, Midnight Lecture. Tonight, we will travel into the endless expanse of space and try to understand why humanity is so drawn to the stars. Space has always fascinated people. Ancient civilizations watched the sky, mapped the stars, and searched for patterns. But only in the 20th century did we gain not just the ability to study space, we gained the ability to go there. Why did this become such an important step? Let's imagine our planet, a small blue sphere in an endless dark ocean, wrapped in a thin layer of atmosphere. This is our only home, but it is not eternal. Earth faces many threats: climate change, resource depletion, the potential impact of asteroids. One day, humanity will have to leave its cradle if we want to survive as a species. However, our drive into space is not only about finding a new home. It is about the desire to explore the unknown, to leave a mark, to pass on a message about ourselves to future generations. We build telescopes, launch satellites, send probes to distant worlds. We want to understand whether we are alone in the universe. Perhaps somewhere among billions of stars, there are other forms of life. But even if extraterrestrial life does not exist, our presence in space is still a way to preserve our civilization. We send not only machines beyond Earth, but fragments of ourselves. DNA messages, plant seeds. If one day humanity disappears, some trace of us will remain in the stardust. Spaceflight developed in leaps. In the beginning, it wasn't just science. It was part of state ideology. The Soviet Union and the United States competed in achievements, investing enormous resources into exploration. This led to an incredible technological leap in just a few years. But over time, enthusiasm faded. Space stopped being purely a matter of national prestige and became also a private industry, where people began to count money carefully. Today, spaceflight moves forward, not only thanks to government programs, but also thanks to private companies that see space as a business. What awaits us next? What discoveries will the new era of space exploration bring? In this lecture, we will look at the history of spaceflight, its technical foundations, and try to peek into the future. So, wrap yourself in a blanket, close your eyes, and travel with me beyond our planet. Space has always called to humanity. Long before the first rockets rose into the sky, people tried to understand how the universe is built. They studied the stars, built observatories, drew maps, but could not imagine that one day they would go there themselves. Yet long before scientists and engineers, dreamers were already painting pictures of journeys to other worlds. In ancient Greece, the philosopher Plato wrote that Earth is surrounded by cosmic spheres where other worlds might exist. In the Middle Ages, people were often afraid to speak openly about such ideas. But in 1608, the German astronomer Johannes Kepler wrote a work called Somnium, the Dream, where he described a journey to the moon. In his story, the hero is carried to Earth's satellite by supernatural forces. Demons transport him through the vacuum, and he sees our planet from above. This was the first work in history where a human being appeared in outer space. Centuries passed, science developed, and ideas about the cosmos became more grounded. In the 17th century, the French writer Cyrano de Bergerac described a journey to the moon using gunpowder charges. His compatriot Bernard Le Bovier de Fontenelle in 1686 published Conversations on the Plurality of Worlds, one of the first serious works discussing the possibility of life beyond Earth. But perhaps the most famous writer to predict space travel was Jules Verne. In 1865, he published the novel From the Earth to the Moon. At that time, no one seriously thought about rockets. The very idea of flying into space seemed impossible. Yet Verne tried to imagine what kind of vehicle could reach the moon. Of course, his spacecraft was very different from modern ones, but it's amazing how accurately he foresaw some details. His vessel was a metal cylinder with a pointed nose. Later, it turned out that this streamlined shape is indeed optimal for passing through dense layers of atmosphere. The shell was made of aluminum, a light but strong metal that would later become one of the main materials for real spacecraft. The capsule in Verne's story was about 2.7 meters in diameter and 3.7 meters in height, close to the size of the Apollo command module used in real lunar missions. Inside, the craft was airtight, just like real spacecraft have to be. For lighting, Verne used gas lamps, and for oxygen, an imagined system that absorbs carbon dioxide and releases oxygen. This is very similar in principle to the life support systems later used on real missions. Inside the sealed capsule were soft couches meant to soften the acceleration during launch, very similar to the specially designed seats used by astronauts to reduce the load during liftoff and landing. The launch method Verne proposed, however, was unrealistic. His spaceship was fired from a giant cannon. In real life, the forces involved would kill the crew instantly. But the underlying idea, a powerful initial push to gain the required speed, was correct. Verne even roughly calculated the speed needed to leave Earth's gravity, and his estimate ended up very close to the real escape velocity of about 11.2 kilometers per second. Later, in the 20th century, scientists realized that a single explosive push is not enough. No matter how powerful one rocket is, it cannot reach space efficiently if it has to carry all its fuel and structure at once. Its own weight becomes the main problem. So the idea of multi-stage rockets was born. The huge rockets we see today shed much of their mass during flight. First, the lower, most powerful engines work, lifting the rocket off the ground. When their fuel is exhausted, that stage is detached and falls away. The next stage then ignites, continuing the climb. This dramatically reduces the total mass of the rocket and makes it possible to reach the necessary speeds without impossible loads. In 1895, Konstantin Tsiolkovsky, inspired by the works of Jules Verne, wrote Dreams of Earth and Sky, where he described the concept of multi-stage rockets and life in weightlessness. Then, in 1903, he developed the mathematical theory of rocket propulsion, proving that rockets can overcome Earth's gravity. In the mid-20th century, his formulas became the foundation of all space programs. The American rocket Saturn V, which delivered people to the moon, had 3 stages. The first accelerated it to about 68 kilometers altitude. The second placed it into Earth orbit. And the third sent the spacecraft toward the moon. The Soviet R-7 rocket, which launched the first satellite, and later Yuri Gagarin, had a different layout, but also used multiple stages to escape Earth's gravity. In the early 20th century, German engineer Hermann Oberth and American engineer Robert Goddard independently came to the conclusion that liquid fuel was the key to building real rockets. But the race for space did not start with romantic dreams. It started with war. Europe, once the center of science, lay in ruins after World War II. The British, French, and German empires were weakened. Their economies stalled. Their armies shrank. But 2 countries emerged not only without devastation on their own land, but also as new superpowers, the USSR and the USA. Their rivalry covered everything: politics, economics, military power. Soon, it reached space. If in the 19th century, scientists dreamed of traveling to the moon, then in the 20th century, space became not just fantasy, but also a tool of political influence. Whoever launched the first satellite, whoever sent the first human into space, would prove to the whole world their technological superiority. Imagine 2 trains racing on parallel tracks. They will never collide, but each tries to be just a bit faster than the other, even by a fraction of a second. That was the space race. One country would make a breakthrough, and the other would immediately try to catch up. In the early years, the Soviet Union was ahead. There was another reason why the USSR and USA were so eager to conquer space: military technology. Nazi Germany's Vi-2 program created the world's first ballistic missile capable of reaching the edge of space and striking distant targets. In 1944, the Nazis used V-2 rockets to attack London. They rose to about 200 kilometers, briefly entered space, then fell on the city. Reaching speeds over 5,000 kilometers per hour, they were almost impossible to intercept. After the war, both the USA and USSR rushed to adapt this technology for their own purposes. A real hunt for German rocket engineers began. Both countries gained access to the remnants of the German rocket program, but used them differently. The United States brought Wernher von Braun, the creator of the Vi-2, over to America. The Soviet Union got Helmut Grotrup. Yet the true future of spaceflight was shaped not by them, but by a man whose name remained secret for many years: Sergei Korolev. Korolev was not just an engineer. He was a dreamer, inspired by the books of Tsiolkovsky and Verne, a man who could turn science fiction into reality. But his path was incredibly hard. In 1938, he was arrested on false charges and spent several years in labor camps under brutal conditions. Only in 1944 was he released and assigned to work on rockets. Later, in the 1950s, he became the head of the Soviet space program. Even after the first successes, his name was classified. Officially, he was simply the chief designer. In the USSR, rockets were built as weapons. The Soviet economy was focused on military development, and war required intercontinental ballistic missiles capable of carrying nuclear warheads across the globe. But if a rocket can reach any point on Earth, it can also go higher. The USSR developed the R-7, the world's first intercontinental ballistic missile. It not only surpassed the V-2, but could also launch objects into space. At the same time, the United States was building its own missiles, Thor and Atlas, but they were less powerful than the R-7. It's important to remember, all these developments were initially purely military. Neither in the USSR nor in the USA did people start by thinking, let's explore space for science. They built rockets to deliver nuclear warheads. Only when they realized that the same rockets could leave Earth did the space age truly begin. Both sides understood. Whoever gained control over space would gain a strategic advantage. But while in America, space flight was one of many areas of science, in the Soviet Union, it became a national ideology. For the USSR, space exploration was not only about science, but also about prestige, a demonstration of the superiority of the socialist system. so the country invested enormous resources in its rocket programs. Spaceflight became state project number one. In the 1950s, almost no one believed a human would fly into space within the next decade. But the technological leap turned out to be so sharp that in just a few years, humanity went from simple rocket tests to orbital flights. On October 4th, 1957, the world changed. The Soviet Union launched Sputnik 1, and for the first time in history, a human-made object reached orbit. It was a small metal sphere with antennas weighing 83 kilograms. It carried no cameras, no complex instruments, only a radio transmitter that sent out simple beep, beep signals that could be heard around the world. Sputnik proved that a man-made object could stay in orbit without falling back to Earth, and it became the beginning of satellite communications. Scientifically, it was a breakthrough. Politically, it was a shock for the United States. America had considered itself the technological leader, but now the Soviet Union had reached space first. In response, the US hurriedly created NASA and began to build its own space program. But the USSR did not intend to stop. If the first satellite was mostly a symbol, the next missions were more scientific. Before sending a human, engineers had to find out whether a living being could survive weightlessness, radiation, and heavy G-forces. So biological missions began. The first living creature in orbit was Laika, an ordinary stray dog selected for the Sputnik 2 mission. On November 3, 1957, her spacecraft reached orbit. The flight was tragic. Laika was expected to live for several days, but due to overheating in the life support system, she died within a few hours. Her capsule was never meant to return. It eventually burned up in Earth's atmosphere months later. The experiment was cruel, but it gave crucial data. Living organisms can survive launch and weightlessness, but a human spacecraft must be designed differently. In 1960, the USSR launched a new experiment. On August 19, 1960, two dogs, Belka and Strelka, flew into orbit and became the first animals to return alive. Their spacecraft spent 25 hours in space. After landing, the dogs were in good condition, proving that a human could survive an orbital flight. In 1958, the Soviets launched Sputnik 3, which for the first time conducted a magnetic survey of Earth from space. The USA understood. The USSR was ahead, and they had to catch up. On January 31, 1958, the United States launched Explorer 1, their first satellite. Its main discovery was the Van Allen radiation belts, zones of high-energy particles trapped by Earth's magnetic field. This showed that our planet is shielded from cosmic radiation by invisible magnetic structures. While engineers were preparing for human flights, another race began. Who would reach the moon first? Again, the USSR took the lead. On September 12, 1959, an R-7 rocket launched Luna 2, the first man-made object to reach the surface of another celestial body. It crashed into the moon and left behind a sphere with the Soviet emblem. On October 4th, 1959, Luna 3 was launched. It performed a flyby around the moon and photographed its far side, the side no human had ever seen. Space exploration has never been a smooth road. We remember the big victories: the first satellite, the first human in space, the moon landing. But behind each triumph stood dozens of failures that are rarely mentioned. When engineers sent the first probes, they simply didn't know what to expect. The moon seemed close, but landing on it turned out to be far more difficult than anyone imagined. Spacecraft crashed again and again. They lost control, fell, exploded during descent. Some even missed the moon entirely and flew off into deep space. For several years, Soviet probes tried to perform a soft landing, but every time something went wrong. Luna 5, Luna 6, Luna 7. One after another, they failed. Sometimes the braking system didn't work. Sometimes orientation failed. Sometimes there were calculation errors. It almost felt like the moon did not want guests. Only in 1966 did Luna 9 finally make a soft landing and send back photos of another world's surface. The images showed nothing but a barren, rocky landscape, but they proved it was possible to land. The Americans also made many mistakes. Their probes failed to reach the moon, crashed, or missed their targets. Some missions to Mars simply disappeared in its atmosphere. One spacecraft reached Venus, only to be crushed by the planet's enormous pressure before landing. It was an era of trial and error. No one yet knew how to build a truly reliable spacecraft, how to land on another world, how to survive its gravity and radiation. All of this had to be learned in practice, losing mission after mission. But each failure brought new knowledge. Step by step, engineers improved their designs, corrected mistakes, refined systems. And eventually, spacecraft not only reached their targets, but also began returning priceless scientific data. The first satellites proved we could cross the edge of the atmosphere. But sending a human into space was another level entirely. No one knew how the human body would truly respond to weightlessness, how the mind would handle isolation, whether the spacecraft systems would work under real conditions. It was a step into the unknown. Training for the first cosmonauts took place under extreme secrecy. The USSR needed not just experienced pilots, but people with extraordinary physical and psychological resilience. They would have to endure huge G-forces, isolation, rapid pressure, and temperature changes. They needed people who would retain control in the most stressful situations. A group of 20 fighter pilots was selected. One of them was Yuri Gagarin. The spacecraft Vostok 1, designed for the first flight, was very simple. It was a spherical capsule about 2.3 meters in diameter, with one round window and a tiny periscope at face level. Inside, there were almost no controls in the usual sense. The flight was fully automated. Manual control was sealed in an envelope for emergencies. The spacecraft was launched atop the R-7 rocket, the same one originally built as an intercontinental missile. It had 6 engines, burned kerosene and liquid oxygen, and had a launch mass of nearly 300 tons. Its fuel load was enough to place the spacecraft into orbit in about 8 minutes and 49 seconds. On April 12, 1961, at 9:07 in the morning, Gagarin, strapped into his seat, heard the command, "Key to start." Seconds later came the legendary "Poyakali, let's go." The engines ignited, accelerating the rocket to about 28,000 kilometers per hour. G-forces reached about 4G, 4 times his body weight. The rocket climbed through the atmosphere, and the spacecraft separated. Weightlessness began. The first thing Gagarin noticed was absolute silence. On Earth, we are surrounded by sound, cars, wind, voices. In space, there was nothing, only the bluish disk of Earth beneath him, and a blackness unlike night sky, pure, airless black. Vostok made one orbit around the planet. The flight took 108 minutes. Gagarin saw thunderstorms flashing on the night side and the sun rising over Earth's horizon. He reported that he felt fine, no serious problems with balance, no loss of consciousness. It meant a human being could survive spaceflight. The most dangerous part was re-entry. To return, the spacecraft had to slow down, but the service module initially failed to separate correctly. For several minutes, Gagarin re-entered the atmosphere with extra mass attached, experiencing strong G-forces while plasma flames surrounded the capsule. He could do nothing but wait. Eventually, the connecting straps burned through, and the capsule stabilized. Even then, the challenges weren't over. Vostok had no soft landing system for the cosmonaut himself. Gagarin had to eject at about 7 kilometers altitude and land separately by parachute. Local villagers saw a bright fireball, then a parachute with a man in an orange suit. When he told them He had just returned from space. They didn't believe him at first. This flight changed everything. The world now knew a human can leave Earth and come back alive. The planet was no longer the ultimate boundary. 2 years later came another milestone. The first woman in space. Valentina Tereshkova spent almost 3 days in orbit, helping doctors and scientists understand how prolonged weightlessness affects the female body. It was a symbolic flight for the world. But the next real challenge was the first spacewalk. Until then, humans had only been inside protective capsules with thick walls and life support systems. One day, however, someone had to step outside into a void where there is literally nothing. No air, no pressure, no sound. Open space was frightening. How would the spacesuit behave? Could a person control their movements in weightlessness with nothing solid around them? Would the oxygen system work perfectly? Any tiny mistake could be fatal. This risk was taken by Alexei Leonov. For his mission, engineers designed a special inflatable airlock attached to the spacecraft. Leonov had to go through it, exit into space, then return. He stepped out, tethered to the spacecraft by a thin safety line. For the first time in history, a human floated freely in space, seeing Earth without the distortion of a window. Below him stretched a gigantic blue sphere covered in clouds and oceans. Around him, total, all-consuming blackness. For about 20 minutes, he worked outside, moving and testing systems. Everything went according to plan, until he tried to re-enter the airlock. The vacuum had caused his suit to balloon so much that he could no longer fit through the hatch. Every second increased the risk of a catastrophe. He had no choice. Leonov began bleeding air from his suit manually, lowering the pressure and risking loss of consciousness. It worked. With great effort, he squeezed back into the airlock and closed the hatch. This spacewalk proved that humans could work in open space, repair ships, build stations, and one day construct habitats beyond Earth. Meanwhile, the United States was developing its own piloted programs. Unlike the USSR, which focused on firsts, the Americans emphasized step-by-step preparation. They understood that their ultimate goal was not just to fly, but to land on the moon. And that would require complex maneuvers, docking in orbit, long stays in space, and precise control. The Mercury program was the first step. Its goal was to prove a human could survive in space and return safely. American astronauts made short orbital flights, just a few orbits, with no spacewalks. They tested life support systems and studied the effects of weightlessness Next came the Gemini program. Now astronauts stayed in space for days and then weeks. They practiced spacewalks, tested docking techniques, and rehearsed controlled re-entry. All this was preparation for the main project, Apollo. The Soviet Union was still ahead in records, but the Americans were steadily closing the gap. Soon, only one question remained. Who would be first to send a human to the moon? By the late 1960s, the space race reached its peak. Satellites were orbiting Earth. Humans had flown in space and walked in open vacuum. And robotic probes had reached the Moon, Venus, and Mars. But the decisive goal was clear: a crewed landing on the Moon. The American Apollo program became one of the largest and most expensive projects in human history. Apollo was not just a spaceship. It was an entire system of 3 main parts. The command module, a small capsule where the astronauts lived during flight, and which was the only part to return to Earth. The service module, a rear section that provided oxygen, power, and propulsion. It was jettisoned before re-entry. The lunar module, the landing craft that separated in lunar orbit, descended to the surface and then returned to dock with the command module. The whole system was launched by the Saturn V rocket, the most powerful rocket ever flown successfully. It was about 110 meters tall, roughly a 36-story building, and weighed about 3,000 tons at liftoff. Its engines produced around 35 million newtons of thrust. Saturn V could send over 140 tons into low Earth orbit, enough for a moon mission. Training took years. Astronauts practiced in desert landscapes that resembled the moon, learned to work in space suits, trained landings, and emergency procedures. Finally, the day came. On July 16th, 1969, Saturn V stood on the launch pad with Apollo 11 on top. Inside were Neil Armstrong, Buzz Aldrin, and Michael Collins. The rocket launched, accelerated to orbital speed, and in about 12 minutes reached Earth orbit. After checking systems, the third stage engine fired again and sent Apollo toward the moon. 3 days later, the spacecraft entered lunar orbit. Then came the most difficult part: landing. The lunar module separated, carrying Armstrong and Aldrin down toward the surface. During descent, the computer became overloaded with data and triggered alarms. On the ground, controllers made a tough decision: continue the landing. Armstrong took partial manual control. With fuel running low, he saw that the module was headed toward a field of rocks. He had to search for a safe spot in the final seconds. At last, the landing legs touched the surface. "Houston, Tranquility Base here. The Eagle has landed." For a moment, there was silence in mission control. Then, an explosion of joy. A few hours later, Armstrong climbed down the ladder. His foot touched the gray dust, and he said the line that would be remembered for generations. "That's one small step for a man, one giant leap for mankind." Humanity had set foot on another world. After Apollo 11, there were other missions. Apollo 12 made a precision landing near a previous probe. Apollo 14 conducted more detailed experiments. Apollo 15 brought the first lunar rover. Apollo 16 and 17 focused heavily on geology and samples. But in 1972, the program was shut down. When Neil Armstrong walked on the moon, it felt like the beginning. It seemed obvious that we would soon build bases there, run regular expeditions, and then move onward to Mars and beyond. Instead, after just 6 landings, the program was canceled, and humans never returned to the moon again. Why? It came down to 3 things: money, politics, and public interest. A moon landing is incredibly expensive. Apollo became the costliest space project in US history. It cost around $25 billion at the time, over $150 billion in today's money. Each launch consumed enormous resources. Saturn V burned about 13 tons of fuel per second. Tens of thousands of people worked behind every flight. Developing permanent bases would have required even greater investment. Once the main political goal was achieved, beating the USSR to the moon, the justification for spending such sums disappeared. In the 1960s, the US spent up to 4% of its federal budget on space. That is huge, especially considering the Vietnam War and domestic social programs. After victory in the moon race, the government decided that money was needed more urgently elsewhere: in the war, in social initiatives, in military technology for the ongoing Cold War. As relations with the USSR began to thaw, the public's passion for space rivalry cooled. Why continue such costly moon missions if the symbolic goal had already been reached? By 1972, the US government concluded that public support no longer matched the cost, and Apollo was canceled. Why didn't the Soviet Union land cosmonauts on the moon? The USSR started its own lunar program roughly in parallel with the US. But unlike America, it never had a single unified plan at the start. Different design bureaus proposed competing projects. There was no single, clear moon strategy. The biggest blow was the death of Sergei Korolev in 1966. He had been the heart of the Soviet space program. Without him, work slowed. The giant rocket meant for Soviet lunar missions, the N-1, turned out to be unreliable. 4 test launches ended in catastrophic failures. Its first stage had 30 engines, and the complexity led to frequent problems. There wasn't enough time, funding, or political will to fix everything. When it became clear that the US had a decisive lead, interest in a costly manned lunar program faded. The USSR shifted its focus to automatic probes and space stations. The moon became secondary. As soon as the Apollo program ended, skeptics appeared. Some people started claiming the landings were faked, that they were filmed in a Hollywood studio, and that astronauts never went there. But this has long been disproven. Modern lunar satellites have photographed the landing sites, including tracks of rovers and descent stages. Laser reflectors left by Apollo crews are still used to measure the distance to the moon. Radio transmissions were received by independent observatories worldwide. Faking all of this would have been practically impossible. The moon landings were real. But after 1972, humanity turned in a different direction. The main priority became long-term stays in orbit, space stations, and later, robotic exploration of the solar system. In the 1960s and 70s, as the moon race slowed, humanity turned its gaze toward other planets. American pioneer missions were the first attempts to leave Earth's neighborhood. Early probes aimed at the moon often failed. But in 1959, Pioneer 4 managed a successful flyby, becoming the first U.S. spacecraft to escape Earth's immediate vicinity. The Mariner series opened a new chapter. In 1962, Mariner 2 flew past Venus and sent back shocking data. The surface temperature was hot enough to melt lead, over 460 degrees Celsius, with pressures almost 90 times higher than on Earth. The romantic idea of oceans and jungles beneath Venusian clouds died instantly. In 1965, Mariner 4 flew by Mars and sent back the first close-up images of the red planet. They showed a barren world covered in craters. Many scientists were disappointed. Mars looked more like the moon than a living world. But later, missions changed that view. In 1971, Mariner 9 became the first artificial satellite of Mars, returning thousands of images. Now we could see giant canyons, dried riverbeds, and massive volcanoes, signs that water once flowed there. At the same time, the Soviet Union was exploring Venus. The Venera series sent probe after probe into one of the harshest environments in the solar system. In 1966, Venera 3 became the first spacecraft to reach the surface of another planet, although it lost contact beforehand. In 1970, Venera 7 became the first to land successfully and transmit data from Venus's surface. In 1982, Venera 13 sent the first color images from another planet's surface. a hellish, rocky landscape under a heavy, toxic sky, where probes survived only for an hour or two before being destroyed by heat and pressure. These missions proved that humanity could not only reach other worlds, but also study them in detail. Before this, everything scientists knew about other planets came from telescopes and mathematics. Now they had real measurements of temperature, atmosphere, and terrain. Photos of Mars revealed ancient channels where water once flowed. Images from Venus showed it was not Earth's sister planet, but a deadly furnace. Many old ideas were shattered, but new questions appeared. If we can send robots, why not humans? Why not land people on Mars or build bases on Venus's high atmosphere? For now, these remain dreams. In the 1960s and 70s, the main practical goal was still the Moon and near-Earth space. Our lecture for tonight is coming to an end. Today, we walked together from ancient dreams about the stars to the first satellites, from wartime rockets to the first human in orbit, from spacewalks to the footsteps on the moon, from lost probes to the first images of other planets. In the next lecture, you will hear about orbital stations, robotic missions, private space flight, space tourism, the future of space, exploration, Mars, the moon, exoplanets. For now, close your eyes, breathe calmly, and let this thought stay with you. We live on a small blue world, but our curiosity has already reached far beyond it. And someday, perhaps, humanity will truly become a multi-planet species. Good night, my dear friends.